Welcome to this walkthrough of LeetCode problem number 1788, Maximize the Beauty of the Garden. In this session, we'll explore how to solve this interesting problem step by step, focusing on the strategies and techniques to maximize the beauty of the garden based on the given constraints. Let's dive in. To solve the problem of maximizing the beauty of the garden, we first consider the brute force approach. This method involves generating all possible subsets of the garden elements and evaluating the beauty for each subset. While this guarantees that we find the optimal solution because every combination is considered, the primary limitation lies in its computational expense. The time complexity grows exponentially, 2 to the power of n, as the number of elements increases. This means that for larger inputs, such as n up to 10,000, the approach becomes entirely impractical. Despite its simplicity and lack of advanced techniques, the brute force method is ruled out due to its inefficiency for large-scale problems. Instead, we must explore more refined strategies that can handle such constraints effectively while maintaining accuracy. Dynamic programming emerges as a more feasible approach for this type of optimization problem. Here, we define a state that represents the maximum beauty achievable for a subset of garden elements up to a particular index, ensuring that all constraints are satisfied. The core advantage of dynamic programming is its ability to eliminate redundant calculations, significantly reducing the computational burden compared to brute force. By carefully designing the state space and transitions, we can systematically evaluate all possibilities without violating the problem's rules. This approach is particularly effective for problems with overlapping subproblems, allowing us to achieve polynomial time complexity, such as n squared, or even n, in some implementations. On the other hand, greedy algorithms were also considered. These rely on making locally optimal choices, for example, by sorting elements based on their contribution to beauty and selecting them iteratively. While this method is faster, often n log n, it lacks the guarantee of finding the globally optimal solution because the problem may not satisfy the greedy choice property. As such, while computationally efficient, greedy algorithms are not suitable for problems requiring a more comprehensive exploration of combinations. The dynamic programming approach is ultimately chosen as it strikes the best balance between efficiency and correctness. By leveraging the overlapping subproblems inherent in the problem, we can reduce the exponential complexity of the brute force method to a manageable polynomial complexity. The key insight lies in carefully defining the states and transitions to ensure all constraints are satisfied while systematically maximizing the beauty. Comparing the trade-offs, brute force is complete but computationally infeasible, greedy is fast but may fail to find the optimal solution, and dynamic programming stands out as the most robust option, achieving both optimality and efficiency. With a time complexity of n squared, or n, depending on the implementation, and a space complexity of n, dynamic programming provides the most reliable framework for solving the problem and maximizing the garden's beauty under the given constraints. To solve the problem of maximizing the beauty of the garden, we first need to break it down into manageable steps. The goal here is to determine the maximum beauty possible, which depends on specific constraints provided in the problem. For instance, the input might be an array where each element represents the beauty value of a flower, and we need to optimize this value while adhering to conditions like ensuring uniqueness within subarrays or limiting the size of the range considered. These constraints help define the structure of our solution. Next, we define the dynamic programming state. Since this problem involves maximizing a value while addressing overlapping subproblems, a DP approach is suitable. Let's define DP, I, as the maximum beauty achievable from the start of the garden up to the ith flower. The transitions between states will depend on the constraints, such as maintaining uniqueness or enforcing limits on subarray lengths. These steps set the foundation for building an efficient and structured solution. Once the problem is well defined, pre-processing can help prepare the data for efficient computation. For example, we might use a hash map to store the last seen index of each flower or a sliding window to maintain the current range of valid flowers. These data structures are essential for enforcing constraints like uniqueness or valid subarray boundaries. Now, as we iterate over the garden, we traverse the flowers array while maintaining conditions dynamically. At each step, we update the sliding window to ensure constraints are satisfied, calculate the maximum beauty for the current range, and update the DP state accordingly. Specifically, dp I is updated as the maximum of the previous state, dp I1, and the beauty of the current valid range. To optimize this process, efficient operations are crucial. For instance, when adding a new flower, we update its frequency in the hash map, and if constraints are violated, we adjust the sliding window by removing flowers as necessary. This ensures that the algorithm runs efficiently, either in linear or near-linear time. After implementing the core logic, it's important to handle edge cases to ensure the solution is robust. For example, we need to consider scenarios like an empty input array, where no flowers are present, or cases where all flowers have the same beauty value, which may simplify or stress the constraints. Additionally, we must test the algorithm with large inputs to confirm it performs well with arrays of size up to 10 to the power of 5 or more, as required by the problem. Once these edge cases are addressed, the final result can be returned. Typically, the result will be stored in dp N1, which represents the maximum beauty achievable for the entire garden. This step ensures that our solution is both correct and efficient for all inputs. Several key insights emerge from this approach. First, the sliding window technique is fundamental for efficiently maintaining constraints. By dynamically adjusting the range of valid flowers as we traverse the array, we avoid recomputing values for every subarray. Second, the hash map plays a critical role in tracking the frequency or last seen index of each flower, allowing for quick updates when extending or contracting the window. Third, dynamic programming ensures that previously computed results are reused, minimizing redundant calculations and improving efficiency. Finally, optimization considerations are crucial. Operations like adding or removing flowers from the sliding window must be efficient to maintain optimal time complexity. Together, these techniques leverage the strengths of dynamic programming, hash maps, and sliding windows to create an effective and scalable solution. The primary data structures used include the dp array to store maximum beauty values, the hash map for tracking constraints, and the sliding window for dynamically managing the range of flowers being considered. To solidify this approach, let's walk through an example with the input array flowers equals 1, 2, 1, 3, 1, 2, 3. We start with an empty sliding window and a hash map. At index 0, we add flower 1, resulting in a window of 1 with a beauty value of 1. At index 1, we add flower 2, updating the window to 1, 2, and the beauty to 3. At index 2, flower 1 repeats, so we adjust the window to 2, 1, maintaining the beauty value at 3. This process continues as we traverse the array, dynamically updating the window and dp state. By the end, the dp array becomes 1, 3, 3, 6, 6, 6, 7, and the maximum beauty is stored in dp 6, which is 7. Analyzing the complexity, the algorithm runs in O(n) time, as each flower is added or removed from the sliding window at most once. The space complexity is O(k), where k is the number of unique flowers, determined by the size of the hash map. This ensures the solution is both efficient and scalable for large inputs. Here, we begin by importing the default dict module from the collections library, which is helpful for handling default values in dictionaries. We then define the solution class and its method maximum_beauty. This method takes in a list of integers, flowers, which represents the beauty values of flowers in a garden. First, we initialize two dictionaries, first_POS and last_POS, to store the first and last positions of each unique flower type. These positions will help us determine the range of indices where each flower type appears in the list. Additionally, we initialize a variable max_beauty to 0, which will be used to track the maximum beauty we calculate as we iterate through the data. Next, we compute the prefix sum of the flowers' values in the list. The prefix _sum array is initialized with one more element than the original list, filled with zeros. This allows us to calculate the cumulative sum of positive values up to any index efficiently. As we iterate through the flowers list, we update the prefix _sum array at each step, adding the maximum of 0 and the current flower value. This ensures that we only include positive values in the sum, as negative values would decrease the overall beauty. We then loop through the flowers list again to update the first_POS and last_POS dictionaries. For each flower type, if it hasn't been seen before, we record its first occurrence in first_POS.
Regardless, we update its last occurrence in last_POS since encountering the flower again means the current index is its most recent position. This setup allows us to calculate the range of indices for each flower type, which is essential for determining its contribution to the garden's beauty. Finally, we calculate the maximum beauty of the garden by iterating through each unique flower type in the first_POS dictionary. For each flower, we retrieve its start and end indices from first_POS and last_POS. If the start index is less than the end index, meaning the flower appears multiple times, we compute its total beauty contribution. This is done by taking twice the flower's value and adding the sum of the positive values between its first and last positions, which we retrieve using the prefix_sum array. We then update the max_beauty variable to the maximum value found so far. Once all flower types have been processed, we return the max_beauty variable, which contains the highest beauty value achievable for the garden. In this implementation, we start by importing the necessary Java utilities and defining our solution class with the method maximumBeauty. The goal is to calculate the maximum beauty of the garden by analyzing the flower array. First, we declare two hash maps, first_pos and last_pos, to store the first and last positions of each flower type respectively. These will help us determine the range of indices for each flower type. Next, we initialize maxBeauty to 0, which will hold the maximum beauty value we calculate, and n to the length of the flowers array. To simplify our calculations later, we create a prefix_sum array. This array accumulates the sum of all non-negative values in the flowers array up to each index. This is done using a loop where we add the maximum of 0 or the current flower value to the running prefix_sum. Additionally, as we iterate through the flowers array, we populate the first_pos and last_pos maps. For each flower type, if we haven't already recorded its first position, we add it to first_pos. We also update last_pos to ensure we always have the latest position for that flower type. These steps set up the data structures and values we need to efficiently calculate the maximum beauty. Now, we calculate the maximum beauty by iterating through each flower type in the first_pos map. For each flower, we retrieve its start and end indices using first_pos and last_pos. If the start index is less than the end index, it means there is a valid range where we can calculate the beauty contribution of this flower type. The total beauty for this range is calculated as twice the value of the flower, representing the flower at both ends of the range, plus the sum of all positive values between the start and end indices. This sum is derived using the prefix_sum array by subtracting the prefix_sum at the start index plus 1 from the prefix_sum at the end index. Finally, we update maxBeauty to the maximum of its current value and the calculated beauty. Once all flower types are processed, we return maxBeauty as the result. This ensures that the solution efficiently computes the maximum beauty of the garden while handling edge cases like negative flower values and overlapping ranges. To solve this problem, we start with an example input, flowers equals 1, 2, 2, 2, 1. First, we initialize four key variables. First_POS and last_POS will help us track the first and last occurrence of each flower type, max_beauty will store the maximum beauty value we calculate, and prefix_sum is initialized as an array of zeros, one longer than the input, to compute cumulative sums efficiently. Next, we calculate the prefix_sum. For each flower, if its value is positive, we add it to the cumulative sum at the current position. For example, at index 0, the flower value is 1, so we add it to the previous cumulative sum, resulting in a prefix_sum of 0, 1, 0, 0, 0, 0. We repeat this for all indices, ultimately computing the prefix_sum as 0, 1, 3, 5, 7, 8. This array will allow us to quickly calculate the sum of any subarray in constant time. Now, we need to track the first and last positions of each flower type. As we iterate through the flowers array, for each flower, we update its first occurrence in first_POS if it hasn't been seen before, and we always update its last occurrence in last_POS. For instance, at index 0, flower 1 is encountered, so both its first and last positions are set to 0. At index 1, flower 2 is encountered, and we record its first and last positions as 1. As we continue, flower 2's last position gets updated to 3, and flower 1's last position is updated to 4. By the end, we have first_POS equals 1 o'clock, 2, 1, and last underscore POS equals 1, 4, 2, 3. Next, we calculate the maximum beauty by evaluating each flower type. For flower 1, its first and last positions are 0 and 4, so we compute the beauty as 2 asterisk 1 plus prefix underscore sum, 4, prefix underscore sum, 1, which equals 7. For flower 2, its positions are 1 and 3, and the calculated beauty is 9. Thus, the maximum beauty for this example is 9. In the second example, we examine the input flowers equals, -5, -4, -3, -2, -1, where all flower values are negative. We initialize the same variables as before, first underscore POS, last underscore POS, max underscore beauty, and prefix underscore sum. This time, when calculating the prefix sum, since all flower values are negative, the maximum of 0 and the flower value is always 0. As a result, the prefix underscore sum array remains 0, 0, 0, 0, 0, 0 throughout the computation. This effectively means that no positive beauty can be generated from any subarray. Next, we track the first and last positions of each flower type in the array. As we iterate through the input, we simply update first underscore POS and last underscore POS for each flower. For example, at index 0, flower -5 is added to both first underscore POS and last underscore POS with its position as 0. At index 1, flower -4 is added with its position as 1, and so on. By the end of the iteration, we have first underscore POS equals, -5, 0, -4, 1, -3, 2, -2, 3, -1, 4, and last underscore POS equals, -5, 0, -4, 1, -3, 2, -2, 3, -1, 4. Since all flower values are negative, any computation for maximum beauty results in 0 because the prefix sum differences are 0 and the flower values do not contribute positively. Hence, the final output for this example is max underscore beauty equals 0. In the third example, the input contains both positive and negative flowers. Flowers equals 3, -2, 2, 3, -1, 3. As before, we initialize our variables. While calculating the prefix sum, the positive values contribute to the cumulative sum, while negative values do not. For instance, at index 0, the flower value 3 is added, resulting in a prefix sum of 0, 3, 0, 0, 0, 0, 0. At index 1, the value is -2, so the prefix sum remains 0, 3, 3, 0, 0, 0, 0. This process continues, and the final prefix sum is 0, 3, 3, 5, 8, 8, 11. This array will help us efficiently calculate the sum of positive flowers in any subarray. To complete the solution, we track the first and last positions of each flower type. After iterating through the array, we have first underscore POS equals 3 o'clock, -2, 1, 2, 2, -1, 4, and last underscore POS equals 3, 5, -2, 1, 2, 2, -1, 4. Now, we calculate the maximum beauty for each flower type. For flower 3, which appears at positions 0 and 5, the beauty is computed as 2 asterisk 3 plus prefix underscore sum, 5, prefix underscore sum, 1 equals 14. This is the highest beauty achievable for this input. Thus, the final output is max underscore beauty equals 14. To analyze the time complexity of our solution, we start by breaking down the key operations in the algorithm. First, we calculate the prefix sum array, which involves iterating through the flowers array once. This requires n time, where n is the length of the array. Next, we populate the first underscore POS and last underscore POS dictionaries by looping through the flowers array again. Each dictionary operation, such as insertion or lookup, averages 1 time. Therefore, this step is also n. Finally, we calculate the maximum beauty by iterating over the first underscore POS dictionary. Since the number of unique flowers can be at most n, this step also takes n in the worst case. The prefix sum lookups during this step are constant time, so they don't affect the overall complexity. Combining these, each step contributes n, giving us an overall time complexity of n. Now that we've established each step operates in n time, the total time complexity of the algorithm is n. Let's shift focus to space complexity, which is determined by the additional data structures used. The first contributor is the prefix sum array,
which has a length of n plus 1, requiring n space. The second contributor is the first_POS and last_POS dictionaries. These dictionaries store one entry per unique flower. In the worst-case scenario, where all flowers are unique, they will require n space. Importantly, the number of unique flowers, represented as u, is always less than or equal to n. Since there are no other significant data structures used, the total space complexity remains n. With both the prefix sum array and dictionaries contributing n space, the total space complexity is confirmed to be n. Let's also consider different scenarios to understand how the algorithm performs in practice. In the best case, all the flowers have the same value. The dictionaries will have only one entry each, but the algorithm still needs to iterate through the entire array. This means the time complexity stays n, and the space complexity remains n. In an average case, the number of unique flowers is fewer than n, but since the algorithm processes every element in dictionary operations are 1, the time complexity is n, and space complexity is n. In the worst case, all flowers are unique. Here, both the first_POS and last_POS dictionaries will have n entries, and the algorithm performs the same operations as in other cases. This means the time complexity remains n, and the space complexity is also n. Comparing this optimized approach to a brute force method highlights the efficiency gains. A naive approach would iterate over all possible subarrays, calculate their beauty, and sum their values. For an array of size n, this would require n squared subarrays, and each computation would take n time, resulting in a total time complexity of n cubed. In contrast, our optimized solution achieves n time by utilizing prefix sums and constant time dictionary lookups. While the brute force approach uses minimal extra space, the optimized solution's n space usage is a worthwhile trade-off for significantly better runtime performance. Finally, let's solidify our understanding with a mathematical proof. In the optimized solution, each element of the array is processed at most twice, once during the prefix sum calculation and once during the population of the dictionaries. Each operation, such as a dictionary insertion or a prefix sum lookup, is constant time on average, or 1. Because no step introduces a higher complexity, the total time complexity is n. This proof confirms that the algorithm is both efficient and scalable, making it well suited for handling larger inputs. When working on optimization problems, one of the most common mistakes is not fully understanding the constraints. Constraints often provide hints about which techniques to use. For example, if the problem limits the range of values in an array, you could use a frequency array for better efficiency, rather than unnecessarily complex logic. Another mistake is relying too heavily on brute force solutions. While brute force can be a useful starting point, it often leads to time complexity issues. For instance, problems with constraints like n up to 10 to the power of 5 require more efficient methods, such as sliding windows or dynamic programming, to avoid time limit exceeded errors. Additionally, failing to handle edge cases like empty inputs, arrays with only one element, or arrays where all elements are identical, can result in runtime errors or incorrect outputs. Finally, overcomplicating your solution is another pitfall. Sometimes, a simpler approach like a greedy algorithm or two-pointer technique solves the problem effectively, while attempting dynamic programming without justification can make the solution unnecessarily complex and harder to debug. Another common oversight is ignoring space complexity. Even if your solution meets time constraints, excessive memory usage can lead to memory limit exceeded errors. For example, creating multiple copies of input arrays or using large intermediate structures can quickly consume all available memory. On the other hand, when approaching optimization problems, recognizing patterns is vital. Techniques like sliding windows, prefix sums, dynamic programming, and greedy algorithms repeatedly appear in such problems, so being familiar with them can help you identify the best solution quickly. It's also important to clarify the problem statement, especially during interviews. If the objective is to maximize beauty, confirm what beauty means in the context of the problem and ask about edge cases. Interviewers often appreciate seeing you outline a brute force approach first to show your thought process, but it's crucial to transition quickly to an optimal solution. Be ready to explain trade-offs between approaches, such as comparing time and space complexities, as this demonstrates a deeper understanding and helps justify your choices.
There are several related problems that can help you build a deeper understanding of optimization techniques. For instance, LeetCode 53, the maximum subarray problem, is a classic example that utilizes dynamic programming or Cadon's algorithm to efficiently find the solution. Another is LeetCode 152, maximum product subarray, which introduces added complexity by requiring careful handling of negative numbers. Similarly, LeetCode 918, maximum sum circular subarray, extends the maximum subarray concept by accounting for wraparounds in a circular array. Lastly, LeetCode 714, best time to buy and sell stock with transaction fee, combines greedy and dynamic programming principles to optimize profits while factoring in additional constraints like transaction fees. These problems not only reinforce techniques but also showcase variations that can arise in optimization challenges, helping you prepare for a broader range of scenarios. There are also alternative approaches to consider and their respective trade-offs. Greedy algorithms are often the simplest and most intuitive choice, especially when local optimal solutions naturally lead to a global optimum. However, they may fail in scenarios requiring a more global perspective or where overlapping subproblems exist.
Dynamic programming, in contrast, is ideal for problems with overlapping subproblems and optimal substructure, but it often comes with the trade-offs of higher space complexity and more challenging implementation. Sliding window techniques are highly efficient for problems involving contiguous subarrays or substrings, but they may not be applicable if the problem requires handling non-contiguous elements. Ultimately, success in solving these problems depends on analyzing constraints to pinpoint the most efficient approach. Handling edge cases effectively is just as important, as it ensures your solution is robust. Finally, in interviews, be adaptable. If an interviewer asks for alternative solutions, such as switching from dynamic programming to a greedy approach, being prepared to pivot demonstrates both flexibility and mastery of multiple techniques. To wrap up, we reviewed how to solve LeetCode problem number 1788 by breaking it into manageable steps. Remember the importance of constraint analysis and edge cases in problem solving. Thank you for joining me today. Don't forget to like, share, and subscribe for more problem walkthroughs. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!